I welcome you to yet another lesson of A-level physics, paper 2, and we are on capacitors. Yesterday, or in the previous lesson, we looked at what a capacitor is, and we said it is the device that is used to store charge. We found that in a capacitor, we must put a dielectric, which can be mica, which can be paraffin, which can be paper, which can be any non-conductor, which can be air. We looked at the uses of dielectrics. We looked at the desirable properties for dielectrics. Then we saw an experiment to show that a capacitor actually stores charge. We looked at the charging and discharging processes of the capacitor, and that's where we had our lesson ending. And we want to continue and look at now that charging and the discharging, because we said that during the charging process, that when a battery is connected across the capacitor plates, as you saw yesterday, then electrons move from the negative terminal of the DC supply, and then they accumulate on one of the plates as it was shown, and then making it negatively charged, as electrons also move from the other plate and they go to the other side of the positive charge, the positive terminal of the battery, leaving the other one positively charged. You can refer to the previous lesson and look at that. And as we said, as the charges pile on either plate, the PD across them keeps on increasing, because we had it in this way. Then we had to put a current measuring device. So we said that as you connect them, maybe you had a switch here which you connect, so electrons move from this and they pile me. If I call this one P and this one Q, so the electrons would actually come here, making this negatively charged, and that would make now the electrons or the negative charges also move from this and they go that side. Okay, so the ones came here and others, so meaning they would leave here excess positive charges, meaning P becomes negatively charged and Q becomes positively charged. But we are saying that as the electrons pile on each, the charges pile on each of the plates, then the PD across them keeps on increasing. The PD across this one, it will keep on increasing until when it is equal to the supply PD. We normally call it the Vs. And when the PD across this is equal to the PD across that, then the flow of electrons will stop and the capacitors will actually be charged to the maximum. They can't go beyond that. And therefore, how does now the PD vary? So the PD across these capacitor plates, it was 0 initially. Here we are saying time. Initially at 0, the PD was 0. It keeps on increasing until a certain time where it stops and it becomes constant, and the PD of that one is equal to the PD of the supply. It remains constant. No matter how long you leave it there, it will remain constant. So this is now the variation of the PD, we are saying, across the capacitor plates during charging and discharging, and this is the charging process. The PD, it will begin from 0, it increases. When it reaches here, when the PD across here is equal to the supply PD, then the electrons will stop flowing and it will not go beyond that. And this ammeter, this meter A, will show a maximum diffraction. At that point, that ammeter gives a maximum diffraction. That's the maximum diffraction it can give at that point. Of course, it will go to 0 after that because current has stopped flowing. Then we said that during the discharging process, you just disconnect this and you connect the wires. Then these electrons will flow and come and neutralize these ones. And as they flow, what happens? Still this one will show a maximum diffraction, but in the opposite direction. This meter, by the way, it is supposed to be this kind of a meter, which has a 0 here, maybe 1, 2, 3, 4. 1, 2, 3, 4, as I may say. So now if it had shown this one here, this time it will show this one, the same maximum diffraction, but in the opposite direction, and it will also become 0 at that point. And as you can see, at the beginning of the discharging process, the PD across these two capacitor plates, it was equal to that because they were charged to that. Okay. So as electrons flow, the PD keeps on reducing because the potential difference, if two electrons go this side, now we have lost now that kind of the potential difference. So as time goes on, this one will keep on reducing, until when it is equal to 0. At the time when it is equal to 0, this one will have actually shown the maximum diffraction and it will stop there. That is the variation of the PD across the capacitor plates during the charging and the discharging process. I know you enjoy this one. Now, we also want to have the graph for the variation of the current. Variation of current during the charging and the discharging processes. Okay? Variation of circuit current during charging and discharging process. The word process is there. We are seeing how does current vary. Okay? So, and these ones we are actually going to represent them on a similar graph. This is the current. This is the time. So what happens when you are charging? We say this one, the current will reduce from maximum, because at the beginning of the charging, more electrons are flowing at high speed, okay? The rate of flow of electrons is higher, but as the PD down there keeps on increasing, the rate keeps on reducing. So the current will flow from maximum until when it is 0. Okay? This is during the charging process. So what happens during the discharging? Of course, this is the maximum current. So at the discharging process, for the discharging, it begins from that, the same maximum. So as you keep on discharging, it will now keep on reducing until when it becomes 0. So this is the discharging process, and that one is the charging process. That is the variation of the circuit current. Because remember, I said the meter is like this. If this is our 0 here, 1, 2, 3, 4. 1, 2, 3, 4. This one can take the negative values, this one is positive. So if at maximum this thing was here, so it keeps on reducing. 4, 3.9, 3.83, until when it gets to 0. This is what we are saying. This one is 4, this is 3, this is 2, this is 1, this is 0. Okay? But now see for the discharging, it will be now, it will also show the same maximum deflection, but in this direction. So I can say these are negatives. So it keeps on going in this direction. It keeps on reducing in magnitude. This is the reduction that we are talking about. Until when it also goes to that, and that will be 0. We want to show the variation of the magnitude of charge stored, how it varies with the PT. Remember, what's the role of a capacitor? It is a device that helps us to store charge. Okay? So when we are talking about a capacitor, you are simply talking about charge. So you can't go beyond before we get the relationship between the potential difference and the charge stored. And we want to see if we increase the potential difference, the supply potential, what happened to the capacitor? What happened to the charge that is stored on the capacitor? That's what we want to see. So that is some experiment. So these ones, you can again take your time and look through. They really look nice, and these graphs, we normally write them. We normally write them. So make sure you get them so well. Okay? I can wrap this, and then we have to go to next. But you don't have to forget that you cannot have your mind that is locked down. That is our slogan at Back Science Education Consultants, where we are saying that the continuity of learning is our breakfast. So before we have breakfast, we first think about, is there continuity in learning? So we are actually saying the experiment show variation of magnitude of charge. Experiment to show variation of magnitude of charge stored and PD across the capacitor plates. How does it vary? We want to use what you call the vibrating reed switch circuit. Allow me first to draw it, since it is your first time to see it. It is a very nice circuit, and you are going to actually enjoy these things. Okay? Here we have the capacitor plates. We're going to see how a reed switch circuit looks. Okay, this one is extended. Then we shall have a point here. We can call it a point X. And then we can have another one here, and we call it a point Y. Can have a protective resistor here, can have a current measuring device, that meter there, and then the reed switch circuit is part of this. There is this kind of a symbol, is written like this. When you look at the sign function, the sign function is like that. So this one is representing that kind of a sign function, and it is meaning it is alternating. Current. Okay, so this is what we are calling the reed switch. circuit. And then we have a DC supply here, and then this is the voltmeter to measure the voltage across the capacitor plates, and etc and etc. So you can see all those ones as I continue to explain. So what happens? We want to see how the magnitude of charge, okay, varies with potential difference. If I increase potential difference, does the magnitude of charge increase or it reduces? So how do we do this? It is as simple as this one will be giving us a certain frequency at which this one will be vibrating. I can call it K. That is my switch. So this K will make contacts at X and Y. First, look at this. What happens if it makes a contact at X? You see, if this K makes a contact at X here, it will charge this capacitor because the circuit will be complete, so it will charge the capacitor. When it makes contact at Y, this one will be disconnected from the PD source, so it will discharge the capacitor. But the rate at which this K is touching X and Y is too high. The frequency is too high. You can imagine, let's say 50 vibrations per second. 50 oscillations per second. So in 1 second it has touched X 50 times and Y 50 times. That is too much. So at almost all the time, it's as if the circuit, the thing is continuously charged and discharged. And as it is discharged, we shall be varying the potential, and then we are going to look at the current that is passing through. So what happens? So this is what happens. So when the switch K is activated at a suitable frequency, let's say F, the capacitor is continuously charged and discharged. That's what I'm saying, by K making contacts at X and Y respectively. The sensitive current ammeter A, the sensitive current ammeter A is observed to show a constant current. Is observed to show a constant current. We shall be calling that current I. That meter is showing a constant current, and that's the current I. And F is constant. Okay? So what happens? If we increase the PDV here, so it is observed that when the PD across the capacitor plates is being increased, the current reading I keeps on increasing. So when you increase the V there, the PD, how do you increase it? You see, this one is a potential divider. It can be moved. That's why you have this arrow. It can be moved up or down. By doing so, you are changing this one. So you see, when you have more. So when you increase that one, we are seeing the current doing what? The current increasing. What is it showing us? We are going to do the mathematics and see actually what happens. Because we are saying that this current is the rate of flow of charge. The current is the rate of flow of, somebody can say, the Q, the T, or Q out of time. Okay? Which is Q times 1 out of T. Everyone knows that 1 out of T is EF, meaning that I is equal to QF. But what are we saying? We are saying that this frequency, this is the frequency of vibration of the reed switch circuit, which makes this one to vibrate, okay, is constant because it is activated at a suitable constant frequency F. So since that one is constant, what is it showing us? It is showing us that the I is proportional to the charge. Okay? Now, what has happened? We have found out that when you increase the potential difference, the I increases, meaning that the potential difference is proportional to I. But the I is proportional to Q. In other words, Q is proportional to V. That's the relationship we are looking for. So that means as you increase the potential difference, the charge stored on each of the capacitor plates will increase. We can remove this one and we put a constant, and you find that that constant is actually C, which C is called the capacitance. Remember, in the previous lesson I used to talk about this one, capacitance. So what is the capacitance? This is the capacitance of that capacitor. The capacitance of the, even from the way I say it, that is the meaning. Which capacitor does it have? How much of the work it does? It depends on the capacitance. And you can see that the capacitance is charged out of voltage. So you can see that actually from Q equals CV. When I make C the subject, will be the charge out of V. That is the capacitance of the capacitor. What is now capacitance of the capacitor? You can see it is the ratio of charge to the potential difference. So the capacitance, and actually they will ask you that question. The capacitance of a capacitor is the ratio of magnitude of charge stored on each of the capacitor plates to the potential difference across them. As simple as that. You will have known what the capacitance is. Then what is now? Because we know unit quantities must have units. So what's the unit for capacitance? The unit for capacitance is called a farad. That's the unit of what? Of the capacitance of the capacitor. Then what is now a farad? What is a farad? You realize that if charge is 1 and the potential difference is 1, the capacitance will be 1. And that's what will give us 1 farad. Will be 1 coulomb out of 1 V. Okay? So what is a farad? Okay? It is the capacitance of that capacitor that stores a charge of 1 coulomb when the potential difference of 1 voltage is across the plates of that capacitor. How beautiful is science, specifically physics. These things are so nice. They are so beautiful. You don't need to miss them, okay? I can give you a summary of what all this is. So I am going back to all this so that you can get what to note down easily. I said, when a reed switch circuit K, when the reed switch K is activated at a suitable frequency F, the capacitor C is continuously charged and discharged by the switch K, making contacts at X and Y respectively. The sensitive current meter A is observed to show a constant current I, where I is d2 dt, which is equal to that, which is equal to that, which is equal to this, and which means that I is proportional to the magnitude of charge, which means that I is proportional to the magnitude of charge. We go on. It is observed that when the PDV across the capacitor plates is increased, that is by making this one touch at different points, the current I increases. And when V is reduced, the current I reduces. shows that the charge Q stored by the capacitor increases with the PD across the capacitor plates. This verifies that the magnitude of charge stored on each of the capacitor plates is proportional to the PD across the capacitor plates, i.e., charge proportional to is actually here. Is proportional to V. Therefore, charge equals CV, where this C is the capacitance of a capacitor. Definition. The capacitance of a capacitor is the ratio of magnitude of charge stored on either capacitor plates to the PD across the plates. To the PD across the plates. The SI unit of capacitance is a farad. The SI unit of capacitance is a farad. And then there we have to define what a farad is. We have to define what a farad is. A farad is the capacitance of a capacitor which stores 1 coulomb of charge on each of the capacitor plates when the PD of 1 voltage is applied across the capacitor plates. I said a farad is the capacitance of a capacitor which stores a charge of 1 coulomb when a PD of 1 voltage is across the capacitor plates. We still have a lot. We are going to have an experiment to determine the capacitance of a capacitor. If I bring you 2 capacitors, how do you determine their capacitances? The 2 plates. This is the capacitor now. How do you determine the capacitance of such a capacitor? We are going to look at that in the subsequent lessons. We are going to look at the different kinds of capacitors. Some are horizontal, some are circular, some are spherical, etc. We are going to look at them and which one is better. And we shall continue looking at now the different things, new terms. And now, what should I tell you? I'm only telling you to remain at Back Science Education Consultants. That is your home, the home of understanding and continuity of learning amidst any challenge. Be good, be bad. We are continuing to learn every time, wherever you are, everywhere. You keep learning. Then don't forget to subscribe. And in case you want this work to be sent to your email, feel free to contact us. We shall send it. We have it on CDs. Those who need it on CDs, you can also receive. Please inform others so that they can get. For those ones, we give at some little cost, which is also for the materials used and whatever is required to produce. But all this material is good. Don't forget to subscribe to our channel, BAC, Back Science Education Consultants. We are here for you. Please remain online. In case of any question, feel free to contact us. One of our contacts, it can be this one. We are not hiding it from anyone. 788-20-53-43. I'm Teacher Course of Back Science Education Consultants. Continue following, continue sharing, continue liking our videos, and when you like it, please show that you have liked it and inform others so that we can all progress. That is it for now. Thank you for studying with us.